Yes. And you will tell us about the importance of being exact, integrability, gauge, black holes, physics, and their correspondence, please.
Thank you very much indeed. Thank you very much indeed to the organizer for this wonderful conference and for this chance to me. This talk of mine will be based on many papers and works in progress with wonderful collaborators Marco Rossi, Daniele Gregori, Ratul Mahanta, and Hongfei Xu, and in particular with actually two papers. One appeared today. Unfortunately, this is not the I didn't have time to put it here with Marco Rossi. So this is a synopsis and also in the end a motivation. So I'll be talking about quantum integrability in the form it assumes in integral and functional equations. So something quite concrete you will see in a moment, you may also know about, but trying to bring you, to lead you to a classical integrability, actually simple classical ODE, ordinary differential equations. In general, we would need actually a Lax pair, so some real dynamical classical system, but we will be even simpler. Why? Because actually this is the only, the ODE is somehow the only thing we need for the treatment of Cyber-Witten supersymmetric and equal to gauge theories, or in the in one omega background. So the class of Shadashvili in technical words. And probably we will touch a little bit something about black holes, although I'm not absolutely an expert about it. And you can find a little bit more on papers. So I'll tackle the problem to reach, to bring you to integral equations for quantum system in a way that you already have partially seen. So what happens, I start from an integral scattering theory in 2 dimensions. So, and at the end of the day, in a nutshell, it reduces to a 2-body scattering. Why? And the 2-body scattering of this sort, in which the mass stay the same, because you have the infinite charges. Why the 2-body? Because if you go 3-body, you have the very famous Yang-Baxter equation. You have already heard about it, which tells us that the order of the scattering doesn't matter. So the n-body scattering process miraculously factorizes into 2-body processes. Okay. Of course, I was probably a little bit too quick. You can have diagonal processes, also non-diagonal processes. So both can be really not, but you know that, not trivial. No, now it's too much. Okay, so let's take now an example. My favorite example. I'll do something with this. So, which is Sinch-Gordon. Okay, you have the coupling constant here. It plays a role in this S matrix. It's the S matrix for the only particle in the spectrum, a scalar particle, and this is the usual parameterization used in the S matrix. Okay, this is just a piece of parameterization. This is an on-shell information, as it is said, infrared, call it if you wish, and infinite size. So if you do better answers with this, as you may think of integral systems, it doesn't work. So because we want to compute finite size things. For doing that, you need a new method you heard about, somehow thought about by Alyosha Zamolodchikov and Klassen and Nemetz at the same time, for relativistic theorists at least, in which you exchange time and space on a cylinder in such a way that you had the S matrix here on a compact space, you move it here and in an infinite space, then the S matrix is a good information. The price you have to pay, of course, is that now you ended up with a compact time. But you know, thanks to Yang and Yang, that you can deal with it, promoting it to be the inverse of a temperature. So you have to introduce some thermodynamics to compute your partition function on a cylinder. You can do it leading order by minimizing the free energy obtained by the scattering matrix. And then on the right-hand side, the same free energy is, the same partition function is given by the leading order, by the ground state energy. you are looking for. Let's hope it works. Yes. So equating the exponents, you get something like this, minimizing the free energy. And for relativistic models, we are stick on that at the moment. The S-matrix of the mirror theory, so the other theory, is the same. So you use the same S-matrix, very simple, and this is the original zamologic of N-class and Meltzer idea. You minimize the thermodynamic function, then you do expect nonlinear thermodynamic Bethe-Ansatz equations. You take the solution and you get the energy as an outcome. In our concrete example, this is the energy. You imagine this is a sort of density, somehow valued with some thermodynamics, and this is the dispersion relation of an energy into dimension, and this is the constraint. Okay, the minimization, the outcome of the minimization. And the interesting fact, also already noticed by Roberto, I think in his talk, is that you have a trace of the scattering theory here in the kernel. Instead, there is this equation, on the other hand, recall you in the driving term that you are dealing with a massive particle traveling on a circumference of length r. Okay, and this is a relativistic particle. Now, this is exactly the same equation, written with a different, just a little different mathematical reparameterization, in such a way to make this passage from an integral equation to a functional one. But this step is not so harmless. Why? Because what I do is quite interesting, and this was really invented by Zamologic, you have already this y here, you define it, and you do a sort of up and down in such a way that you cancel the driving term. And on the right, you get the bootstrap of these two kernels. This is a peculiarity of this model. Usually, you don't have a second object here. You have only one, or a product of the same theta. You may have already seen this kind of things. And already this form is very interesting. And both functional and integral equation constrain form and expansion. The expansions give you the conserved charges we start with of the solution. This is the strength and power of quantum integrability in a nutshell. So now we should try to introduce an ordinary differential equation to describe this system. I have to preface that there was already on the table a very beautiful derivation in the case of a Schrödinger equation with polynomial potential of functional equation characterizing minimal conformal field theory due to Patrick, Roberto, Marciano Lugano Zamologic, and many other people among those also myself worked on. But for gauge reason, for other reason, we need here two irregular singularities. Instead, you know very well, with a Schrödinger equation, with potential, you have only one irregular singularity at infinity. Like in the Seiberg-Witten differential, for instance, okay? This is an idea. And also because we want to we want to jump into the realm of Euler equation, okay? Trying to do something like a geometric function in the Euler equation realm. Of course, we elaborated a theory, but it goes beyond of this talk. A general theory to invert somehow this arrow. This is also a work in progress partially. So to take an integral model and to get to an ODE. But this will bring us to really to a couple of lax operators, something like an itching system alla Gaiotto-Mureniesque. So it's more complicated because in general, you get the massive system, okay? Instead, here we are somehow conformal. Okay, we will start with something more heuristic and simpler. So first of all, we notice that Y is beautiful, but actually we expect the spectral determinant to play some role, and Y to be some composite object in terms of this spectral determinant we call Q. And the heuristic idea is that we know already a functional equation in quantum mechanics. We know the unitary condition between the reflection and the transmission coefficient. This can be read off as a sort of, say, functional equation. Okay, let's try to be effective, and Seiberg-Witten theory can be of some help here. Why? Because the original Seiberg-Witten idea, made very, how to say, simple, very simple, is that to take, consider here not, this is already a quantization, consider here the momentum, so really the classical Seiberg-Witten original idea. So you have a differential. Their idea was using a suitable differential, and you make the integration around a cycle, and you get the electric period. Then you invert this relation. U is the energy, if you wish, but also in gauge theory is the trace of the square of the field, or the Coulomb branch modulus, and you put the U in terms of A in the dual period AD, the same integral, the integral of the same differential, but on the other cycle. And in this way, Seiberg-Witte tells you that this is the differential of prepotential with respect to A. So you get, in the end, the prepotential. The same, at least in principle, can be done using the quantization with omega background, only one, epsilon 1, and you have to start with, instead of a differential, with an ordinary differential equation, a Schrödinger-like equation like this. In this case, for pure theory, SU2 theory, this is exactly the Mathieu equation, which is periodic, and the solution, as well known, satisfies this interesting Floquet movement with this phase. But let's focus on functional equation. Let's try to derive functional equation basically for this equation, which means for the periods. First of all, we have to recast a little bit the equation in such a way that is more suitable for integrability, okay, and just changing the potential to be a confining potential, and getting a map from gauge on this side. You have here the omega background deformation, the instant-on coupling. This is the rapidity in integrability word, and this is Coulomb. Okay, so can we use this to be compared with quantum Saint-Gordon? Not directly. You have to introduce at least in a suitable way, using some B goes into 1 over B symmetry. You have to introduce the coupling constant. You make it more complicated, and then you can analyze this equation because you have made effective these two symmetries. The ingredient of this theory is to have discrete symmetries I've already shown you, which are broken by these fundamental solutions. These are the solutions going to 0 uniquely, to 0 at minus infinity, plus infinity. Of course, if you act with ones with the symmetries, you go from U0 to U1. U1 is the exploding one, and similar for V1. Okay, and in this way you get also rigorously the exploding solutions. Now, of course, you define the Wronskian of these two solutions, and this is the spectral determinant. And thanks to the way in which we define the symmetries, the equation has this symmetry, you have, thanks to this definition, you have this. This is the link between the U basis and the V basis, okay? And these are the connection coefficients. The lambda symmetry gives you this translation, and then if you act on this equation with the omega symmetry, you get the second one. And this is the change of basis. So, in other terms, this is Q is the connection coefficients. Then you can construct also more complicated connection coefficients. People working on exact WKB research, they know this very well, which actually are Wronskian in different anti-Stokes sectors. But I don't want to be so complicated, although we need we will see in a moment, but anyhow, you can do it. Then, as promised, we do the final step. We take, as in the course of quantum mechanics, the Wronskian of the left-hand side and the Wronskian of the right-hand side. We get the QQ system, okay? And this will be, in the SFT, might be called also quantum spectral curve under many respects, okay? Now, the return of the Y system. Why? As said, the Y system is a composite object. You have to multiply to Q, it's quadratic, and then you get exactly the same Y system before from the QQ system. So it seems that actually we have got a differential equation fully equivalent to a field theory. The point is that the Y system is the same. The solution is the same. This is a delicate question. I don't take time. And the answer is not, because there is this tricky point here in the inversion of the right-hand side of the Y system. So the path cannot be inverted, but still is you can check carefully. It's the massless limit of Sinch-Gordon theory. So it's Liouville field theory. is this, you see, there is only one exponential, not two, which is good. This is what I promised. So we get only conformal field theories with only one ordinary differential equation. And actually, we see the gauge theory only at the so-called self-dual point, B equal 1, okay? And this is the map. Only at this point you have also the gauge theory interpretation. For this point, we found this beautiful interpretation of the transfer matrix in integrability in terms of the electric period and the Q function, okay, in terms of the dual gauge period, the monopole. Now, if we elaborate a little bit, this is the original Q system in integrability in gauge variables, we get this. We invert now this, and now the TBA equations are twofold. There are two pseudo energies, U and minus U. And this gives us already the spectra, the spectra of Seiberg-Witten theories at strong coupling. This is the monopole, and this is the dione. But actually, going from there to weak coupling, so to recover A, the electric path is a complicated fact. People know that there is wall crossing and so on and so forth, but integrability gives you a sort of shortcut. There is another relation, the TQ system, and which is a sort of fusion between the weak coupling and the strong coupling. Now, the conserved charges are in the expansion of these quantities when theta goes to plus infinity. You get, this is the usual story in integrable theories. And also, elaborating a little bit, in this way, you find the so-called quantum periods. At zero order, you get Seiberg-Witten and then the quantum correction. But now we want to focus on the other regime, which is the one in which you have the instant-on expansion, which is instead not asymptotic but converging, okay? When lambda, instant coupling, goes to zero. This is the Nekrasov-Okunkov expansion. So where is the prepotential in this picture? Is inside the connection coefficient. If you write the connection coefficient in this form, which seems a little magical, but I'll show you why, AD appears here. And from AD, you have already the prepotential thanks to Seiberg-Witten geometry, to this relation. How do you discover this? You use this as one way is you use this as an answer. The QQ system played in the equation for the dual period, and you can solve it. And you show that the, say, prepotential by Nekrasov and Shadashvili give you the unique solution of this equation. Another more instructive way is to look at new objects here. I'm introducing now the ODE-EN, instant-on correspondence, the Floquet basis. The Floquet basis is new in the integrability world somehow. You have that in the Floquet transform in this way under a period, okay, you can ask what happens if I go the same but from minus infinity to plus infinity. It acquires similarly a phase. This phase, you can prove thanks to this functional equation, some tricks, is exactly the dual period. So it's the phase acquired transversally by the same Floquet function. So we have discovered where somehow the prepotential lives in this picture more directly. And so this means that we have an expression for phi, and we can make many computations. This is not so easy, at least it's more complicated than computing the Floquet, because the Floquet is an integral, as you well know, over the quantum momentum on a compact interval. So Y is finite. Here for me now, instead goes to, apart from the regulators I have to put because these are exploding objects. But anyhow, I have to go from minus infinity to plus infinity. So it's not so obvious to make this kind of calculation. In fact, we use a method which is somehow a reminiscence of what, so it can be called kink method, but and it's quite, so I have no time to go into details. But we learned an important lesson from gauge theory. We learned that it's better to compute phases, to compute the exponential, so the quantum momentum instead of the wave function. And this quantum momentum actually is given in terms of a convergence series of this kind, okay? And there are two kink intervals. This is a little bit technical. I can't go into details. And actually, there is, thanks to AGT, there is AGT correspondence. There is the fact that, and we checked that, people people discovered that the wave function, at least they should be quivered by some quiver, and we check that. The quiver gauge function is an extension. The partition function is an extension of the gauge theory we started from, because it's a quiver. Now we implement the idea to go using this extra phase from the Floquet basis to the decaying phase, from the Floquet basis to the decaying basis, and of course this is done by calibrating in such a way that the Floquet which are exploding they cancel the divergence, and you get this change on basis, making the Wronskian of this side and the other side. You get the relation at the beginning. Actually, this is more general. This holds for any Euler equation. Okay, if you use, you can compute this in the specific case of Mathieu equation, and you exactly obtain the result I promised. But you can do it more generally for any Euler equation. Okay. And we also have all the ingredients computed, 3 ingredients, 1, 2, 3, to write down these two functions. And there is also a better understanding of what people call the Floquet approximation, in which you see U0 is directly given by this Floquet discharging fully this other piece, because this is a non-perturbative correction of this kind. It depends on why you cannot be too close to the so-called horizon. Okay, this is just how much time do you have? Okay, so this is a little bit of say very briefly what happens for when we try to use these things, but very oversimplified thing, when we try to use this thing for black holes, say that in general, so we will talk about a little bit about Schwarzschild and Kerr, and this is again for Schwarzschild. So you have, if you perturb your Schwarzschild metric with a scalar, electromagnetic field, or the graviton, you get a partial differential equation. So these people discovered that this partial differential equation at first order, there are many subtleties, anyhow, can be separated into radial and angular part. So, and for instance, if you do this with a sort of simplified model, although many people, Gubser and collaborator, but also Massimo Bianchi and collaborator, worked on this model, which is more a sort of brain, black brain instead of black hole, and you have this equation, which is the radial part of the Regge-Wheeler, if you wish, in the Schwarzschild, the analogous of the Regge-Wheeler in the Schwarzschild case. And if you do this map, you end up with this equation. They knew already this. The crucial point we observed is that the function we used in integrability are exactly the ingoing function at the horizon and the outgoing at infinity. So are exactly those functions. Now, if you add flavors in to the gauge theories, you go to more realistic black holes metrics. For those, we have also new Y systems and TBA equations. In particular, in the recent time, we focused on NF equal 4, and then we made the confluence to NF equal 3. This is the number of flavors you add in the gauge theory, in which you have exactly this equation. And for this equation, we are really able to tackle the problem of the Tukowski equation for Schwarzschild and Kerr or Regge-Wheeler. And of course, there are people that instead of using integrability, I have to mention this, that there are many, using gauge instantons calculations to tackle these black holes computations using the partition function. But often they have to have information about the wave function. They have to enlarge the gauge theory to be a quiver gauge theory, so with a more complicated, say, gauge group. So quasi-normal modes in a slide. So you may have already understood that quasi-normal modes arises when you impose your solution, the boundary conditions to be like V0, but also U0. So you are imposing this to be 0. But this is exactly the same condition with which we define beta roots. So quasi-normal modes in this picture, although complex, are nothing but the beta roots of the quantum integrable model. And this is a slide which tells you that this is the only the TBA for the integrability, gives you the spectral determinant, and the spectral determinant enters in the end the waveform, so the solution of the partial differential equation. And maybe this could be of interest for calculations also in gravitational physics beyond and not only in gauge theories. There are some conclusion and perspectives. So I think I leave time for questions if there are, and I would like really to thank you.
Thank you. So are there any questions or comments for Davide Fioravanti?
There is one over there, I think.
Hi, thank you for the talk. I just wanted to ask, I mean, the thing that you started with, I mean, is sort of well known to correspond via, say, Nekrasov, Rosli, and Shatashvili to semi-classical Liouville, because you're in this Nekrasov-Shatashvili limit somehow. Yet now you get this self-dual Liouville instead. Can you say something about this?
Absolutely. So yes, very good question. It seems so. Yeah, this is not the IGT correspondence. What you mentioned, that the semi-classical Liouville, C going to plus infinity, just to be even more explicit, since I like to be explicit, is true in the IGT correspondence, no? Like instead the self-dual is C equal 1. Is the other. We have also information about self-dual. I don't have time because we have the blow-up equations. Our reveal is a little bit mysterious because actually I have a question for you. What is our Liouville for b different from 1 doesn't have any correspondence in gauge theory. So it's somehow orthogonal to the IGT1. It would be beautiful, although it's not true, that B is the other omega background, epsilon 2, but it is not the case. It's too simple, because you know that you have a partial differential equation, Belavin Polyakov-Zamolodchikov, basically, for the general backgrounds. So it's another Liouville, and it will be interesting to understand how can be interpreted fully in terms of gauge theory. We don't have this interpretation. Only one point, which is special, deserves of this calculation. And actually, there are, of course, instead, the integrability theory is valid for any B. But what is missing in the integrability theory, to be honest, is the prepotential. So the prepotential solves somehow what is technically called direct and inverse monodromy problem. Instead, for B different from 1, you don't have the prepotential. Or better, we should work on this to find the prepotential. The formation of the Nekrasov-Shatashvili prepotential. I don't know. Also, the instanton expansion will be delicate.
Okay, any further questions? If not, let's thank David once.
Thank you.